In this video, let's take a look at the properties of the insertion sort algorithm. As an overall note, this is complicated. Okay, so this requires maybe a little bit more intuition than I would expect from you guys on something like an exam. This is a little bit tricky here. So let's walk through this and see what we can get. All right, so we have insertion sort. The code is down here. I've made it a little bit shorter just so it's on the slide. It's 3 lines. 3 lines though that are, well, they're going to be tricky because they depend on the data. That you probably already suspected because of the previous examples, right? If you're looking about the visual traits we looked at, well, that input that was in reverse order, that took a lot more work than the one that was nearly sorted. So our algorithm now, right, is highly dependent on basically how it's sorted, right? How much work it does is dependent on how sorted that input array is. All right, so again, we'll start with this kind of picture on the side, another diagram basically to show, those 2 nested loops, because we have a loop here and a loop here that kind of run n times. It's going to be tricky here. But here, right, basically gives us this picture over here where we have n by n, right? Certainly the I part isn't too bad because it's like, well, I have I elements, I need to sort each of them. So this is kind of I over here, and this is going to be j on the other side. So the way this trace is basically written, right, is that the gray stuff is elements that don't move versus black elements are elements that are being moved around. But initially, right, we basically start with a case where it's like, well, everything is unsorted, right, except for that first element. And then we gradually have to go through O, R, T, right? We're going to basically go and shift them to where they belong, right? So it's like over here, O is fine. So over here, right, O is fine. Then we get down here. Oh, so position 0 is fine with O, right? Then position 1, well, that has an S, and it should be swapped with an R. And so we kind of walk down here along the diagonal, right? We're basically looking at all the different elements, right? Trying to sort them one at a time. So this somehow, right, has the flavor of that triangle thing from before. Where we were saying, oh, hey, I'm doing this work, this work, this work, and each time I'm doing a little bit of this work, right? Because somehow, right, it's like I have my 2 inner loops, right, and there's a dependency, right? So the outer loop is an end loop, and the inner loop, right, kind of depends, on the outer one, right? So j is dependent on I is by itself, right? So I is fine, it just goes from 1 to n, easy. But j has some sort of dependency on I. And it does basically, well, in this case, it's actually doing more work each time. It starts because if you think about insertion sort, right, when you start, first element you want to insert, you only have to move it so far. Next element you have to move a little bit farther. Next element a little bit farther. Next element a little bit farther. Next element a little bit farther. It gets more expensive each time. And so actually, kind of to complete this picture here, this is kind of our triangle of work that's happening, right? So these are all the comparison stuff that we're having to look at on the left side. The gray stuff we're all kind of just leaving it alone. The gray stuff is where we're going to be picking out those elements on the diagonal and then shifting them to where they actually belong in the input. Left side is where my work is really happening, right? So you can notice that the letters inside are constantly changing, right, as I insert things into that sorted region. So my work becomes more and more each time. So it's like this time, right, you only need to look at, maybe 1 element, then 2 element, 3 element, 4 element, right? The work I'm doing each time increases. So yeah, maybe at a glance, right, what I thought would be there is that it's going to be, n squared over 2, based on that, right? Because I have basically loop by loop each time, I'm doing a little bit more work, a little bit more work. It's basically just the flip side of doing, less work each time. Yes, but we do a little bit more work on top of this. So the more work. Well, really what we want to do is know a little bit more about how this thing does the insert. So we want to know how many insertions, how much we'll have to move an element, okay? And this is where our cases come in. So let's suppose that we have randomly ordered input. Well, if I have a randomly ordered input, right, so like imagine I have a randomly ordered input, right? So let's say I have this here, right? So I have this array. I'm working in the middle, right? This is completely random. So this is unsorted, sorted. This is basically random over here. Random. Well, this is random, but it's been sorted. What happens though is that because I'm looking at, so this is my unsorted region on the left-hand side, right-hand side, right? I'm looking at this element here, and it's like, oh, it's unsorted. I want to put it where it belongs. It's random. Basically, what that means is it has kind of a chance of going anywhere, right? So it should be something that could insert there, 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 something, right? I don't know whether it's going to be something I insert early or I insert late into that sorted region because it's coming from this stuff that's basically just random, okay? So I could insert it, it could be done, right? Maybe I don't have to do anything, or maybe I have to move it all the way to the end. And so this is actually, well, so this is okay, right? This is actually okay if it's random input. Because sometimes I'll win, I'll be able to place it really soon. Sometimes I'll lose, or I'll have to go all the way to the end. Basically what happens is, right, is if you think about basically some arbitrary line here, the expectation is, right, if it's random, that I visit half of those elements to get it to where it belongs. So I have basically a 1/2 factor there because that's on average how many things it'll need to look at, okay? And that actually plays into my analysis of algorithms. So that'll actually give me this over here. So notice over here I have n squared over 4. That's coming from basically n squared over 2 for that triangle thing, times the 1/2 factor for every time I do my insert, I have to walk through half of that array, right? I have to walk through half of the sorted region. And so yeah, that's what I end up here for insertion sort. And I get basically the exact same thing for exchanges as well. These two things are basically linked up, because every time I do a comparison, I'll have to do an exchange. Right? Those two things are linked together. There's no if statement, there's no guard there or anything else. Those two things are linked together. Probably I'll end up having one more comparison than exchanges, but like that's fine. It's just a constant amount. Who cares? So yeah, we end up with basically our n squared over 4 for both comparisons and exchanges based on this thing over here, right? So think of that triangle. You're only working one side. You're doing more work each time, and then each time you're doing work, there's expectation that you are done, halfway through that row of finding out where that thing should be inserted. All right, so that's what we got for that one. Jumping now, we can basically have the same logic for the reverse case, except that we don't get that 1/2 assumption. So that 1/2 assumption came from the fact that this is basically a random number we're inserting, so it could go either early or late. Well, if it's in reverse, we know that element we're inserting is going to be the one that's on the far side. So we're going to have to walk the entire thing. So basically, this, we're going to have to go from here all the way to here. So this is equivalent of saying we have now a factor just of 1, right? We don't get to save any time. We're never going to be done early. So in that case, right, we don't get another 1/2 factor, and so we're stuck here with this n squared over 2. That's what we get for reversed, right? And then for reverse, right, same thing basically gets mapped over to exchanges because, well, those two things are hand in hand. So same number there. So there we go. So that's random input and then reverse. I know again, right, the random one is a little it's a little bit complicated, right, to do the triangle thing plus to be able to know that, oh, hey, the expectation is that you find it halfway through the row, so that you get extra 1/2 factor, right? That's a little bit of a jump, but yeah. All right, last case we have here is of course the best case. So let's take a look at that. Best case, this is easy, right? If the arrays are already sorted, no exchanges, duh, right? I mean, what else would it be? You can't do exchanges if it's already sorted. At least insertion sort won't. Selection sort will, right? Selection sort always does the same thing, so we'll have like n exchanges, but insertion sort is smarter. It won't do any exchanges. For comparisons, this is basically, we have n comparisons because in any case, right, our algorithm is going to have to go and look at every single element at least once, right? We need to verify that it is sorted, right? You're not going to be able to have a sorting algorithm that works in less than n comparisons because then you can't even verify that it is sorted, right? You can't do anything whatsoever. So yeah, we'll have to have n comparisons, n minus 1, because it comes from the fact that we can start here, right? We're starting at that one position instead of starting at the very beginning. But yeah, that's pretty good, right? So this is kind of your idealized, right? So your worst case, right, is this over here, this reverse case, right? Best case is sorted. Average case, right, is just random in between. And if you have something else, right, if you have something that's like nearly sorted, well, think about it. Nearly sorted means that it'll probably look like the best case, right? So it's like if you have something that's kind of similar to these three, ideal cases, it'll probably act like one of those three, right? So it's like if I have something that's almost completely random, it'll probably act like random, right? If I have something that's almost completely reverse, it'll probably act like reverse. So these are the three kind of main ones, right, that have the most performance difference and kind of represent the different ways the algorithm may act depending on different inputs. So yeah, there we go. 3 different approaches, right, to analyzing this algorithm based on different inputs.